Hello everyone, it is definitely my pleasure to welcome you to my talk at this online conference. My name is Dmitry Soshnikov. I work for Microsoft as Cloud Developer Advocate. So my role now is to provide the communication between developers worldwide and the developers at Microsoft who actually develop our products. And before that, I was a software engineer specializing in artificial intelligence and machine learning. And that's exactly the topic I will be talking to you about today. So today I will talk about two things. First of all, it's our tool for machine learning called Azure Machine Learning. I will show you what's the best way to start using it, and then I will show you how to use Azure Machine Learning to produce some interesting results, how to generate paintings using generative adversarial networks. About Azure Machine Learning. In artificial intelligence, the most important thing is to be able to train big neural network models. And for that, we need a lot of cloud resources. And that's why cloud is used very nicely with all AI tasks. And in Microsoft Cloud, there are several layers of technologies which are related to AI. First of all, of course, it starts with the infrastructure, because in any cloud you have the possibility to create virtual machines with powerful compute and with GPUs, which are very useful for training machine learning models. But working on infrastructure level requires a lot of efforts from developer, because you need to pay attention to the configuration and you need to do some infrastructure tasks which are not really interesting. And that's why it's more interesting to be using platform models, platform services. And our best platform service for machine learning is called Azure Machine Learning, and that is the topic of my talk. I also want to mention that apart from that, there are services which contain pre-trained models. For example, if you need to solve some typical tasks, such as recognizing objects in the picture or determining people, checking faces, emotions of people, age, and so on, you can use pre-trained models which are called cognitive services. And those pre-trained models, they are available for vision-related tasks, for speech, for working with language, for things like OCR, machine translation, and so on. And using those services, in fact, can solve a lot of business problems, and you can use them without the deep knowledge of AI technologies. But let's switch to Azure Machine Learning. Azure Machine Learning lies in between infrastructure services and pre-trained models, because it gives you full flexibility to train anything that you like, but you don't need to worry about low-level details, such as how to install libraries, how to maintain their latest version, and so on. All those things that you would need to do if you were using virtual machines. Of course, you can also use virtual machines, because it's very easy to power up a virtual machine which contains all pre-installed versions of most popular neural network libraries. But that provides much less flexibility. So again, Azure Machine Learning is uniquely positioned because it's our central tool for AI model training, and it is targeted both at advanced data scientists, which have very demanding tasks like parallel training on several machines in the cluster or handling a lot of data. And there are also features for beginners such as AutoML and Visual Designer, which allow you to start using this tool even if you are not a pro, even if you don't write everything in your code. So to start using Azure ML, you need to change a little bit the way you think about machine learning, because for a data scientist, of course, it's easier to use familiar tools such as Jupyter Lab, Jupyter Notebooks, and that's why in using Azure ML, there is a sort of learning curve that you need to make in order to start using it effectively. And the best way to start using Azure ML is to use Visual Studio Code, because as I will show you shortly, it's as easy as just taking the script and running it on the cluster with a few clicks of a mouse. So this is the very good way to start, and I wrote a blog post about that, the best way to start with Azure ML using VS Code, and you can check it out, and it contains step-by-step instructions, and I will also show you some of them today. There are also other things that you can use Azure Machine Learning for example, to optimize hyperparameters, and to train language models such as question answering models. Those are topics that I have the blog posts about, and I encourage you to continue learning more about Azure ML after this talk in my blog. And I also have the GitHub repository with samples which contain step-by-step instructions, so you can use it as a tutorial to begin experimenting with it yourself. So let's start with talking about what Azure ML is. First of all, it's a container which encapsulates everything which is related to machine learning. For example, when you want to train a model, you need to start with a data set. So you need some storage to store this data. Then you need some compute to train the model on. And all that can be stored in one central place, so that you don't need to remember that you put the data in this drive or in this storage account. You just have the workspace, and everything related to your problem is located there. You also have the ability to store and run Jupyter notebooks. You have the ability to store the results of all experiments. Whenever you start training a model, normally you would repeat this training a lot of times, and you would record the best accuracy that you were able to achieve. And Azure ML can do it for you. It can store all the experiment results. It can store models. You can then select the best model and deploy it. So all this process can be done from Azure Machine Learning. Now let's see how that works in real life. I will start by creating an Azure Machine Learning workspace through Azure Portal. So it's as easy as selecting Machine Learning, clicking Create. Then you need to provide some name for the workspace. Select a resource group. Resource group is something which groups cloud resources together so that it's easier to manage them, like to delete them, to track spendings and so on. Then I select the location and the workspace edition, which can be basic or enterprise. We can start with the basic one. And then I click Create. Once it's finished, the first thing I need to do, I need to launch the separate Azure ML portal, because Azure ML portal is the redesigned, improved way to interact with all machine learning resources inside the workspace. So this portal, the first time you run it, you need to select the workspace you want to use, and that's only you need to do it for the first time. And then you can see that here you have everything in one place. Like you have a section for notebooks, for datasets, for experiments, for pipelines, for models, and so on. Let's start by creating a compute which we will use later on to train the model. So I go to compute clusters, give it some name. I can then select the machine type, either CPU or GPU, and I can select low priority virtual machines, which would be significantly cheaper than using the normal virtual machines. Low priority machines can be taken away from us at any time, but then the cluster would recreate them, so it's not really a huge problem if you are doing the training in the Azure ML. So now you see we have created the cluster with 0 nodes by default. But as soon as I start training, it would automatically resize and add additional nodes, which we can use to train our model. Once we have created the compute, we can use it to run some machine learning experiments to train some models. The way it works is we create the Python script which performs the training, and we submit it to Azure ML as an experiment. And the good thing about it is that the experiment would automatically take the machine on the cluster which is not used, or it would be queued if you have several experiments waiting to be executed, and it will be automatically scheduled to the available machines in the cluster. Another very interesting thing is that you can keep track of all experiments by logging their metrics and by storing the models produced as a result of the experiment. So the way you do it is you add a little bit of code to your Python training script, which logs the result. For example, after you train the model and achieve some accuracy, you can say run.log accuracy, and it would store the achieved value of accuracy together with this run of the experiment. You can then submit the same script, for example, with slightly different parameters, and it would also log the results so that later on you can just browse through all the experiments that you performed, select the one with the highest accuracy, and take the corresponding model. As an example, let's take very traditional data science task, which is handwritten digit recognition using MNIST dataset. You probably know, if you did some data science, that MNIST dataset is the dataset of about 60,000 of small handwritten digits, and this dataset is so good that you can use almost any machine learning method to train it. So let's see how to train it on Azure ML. So I will start by opening the script in Visual Studio Code. I will use the scikit-learn for doing the training, and you can see that I can run this script locally on my local computer. It would train the simple logistic regression model. That doesn't take long, and we immediately achieve the accuracy of about 90%, which is not too good, but also not too bad. If I want to run this on Azure ML, I add this code for logging metrics. And then from VS Code, it's as simple as right-clicking and selecting Run as Azure Experiment. Then I need to select some parameters. For example, I choose the subscription, I choose the compute Azure ML cluster, which we have just created. Then I also select the environment. In our case, I'm using scikit-learn, so I select that I want scikit-learn. Then I provide, if needed, some reference to datasets, but we are downloading data from internet, so we don't need that. And then I have the description with all the dependencies here in the JSON file. I just click Submit the experiment, and here it is. It submits this code into Azure ML. So what happens is that the current Python script and all the directory which might contain some other dependencies is submitted to Azure ML. And now the experiment is being executed there. I can open it in the portal. And I can see here it's being queued. So right now the cluster is being scaled to create the first virtual machine. It will take some time. I have the secret time machine to speed this up. And once it started running, you can check the log file of your script here in the outputs plus logs. That's the good way to debug the script, because you do not see how it executes interactively. You can see all the logs here. Here you see that this is fetching MNIST data is something that my Python script prints in order to let me know what goes on. If I have some errors, for example, if I forgot to specify some dependency, this error would show up here either in this script or in some earlier ones. Once the model has finished, I can check and see the accuracy. This is the accuracy that was logged by our script. And I can then, if I have several runs, I can display them in one list and look for the accuracy in this graphical form. So if I have many experiments, it will show me how the accuracy goes, and I can select the best one. So let me summarize how the experiment submission works. I work from my local computer, and when I submit the experiment, it snapshots my current folder together with all possible additional Python libraries that I might be using in my script, and sends it to the Azure ML. From that directory, the Docker image is created, which starts from the standard Python image, installs all required libraries specified in the JSON config file, and the container image is stored in some container registry. And then the actual process of submitting the experiment begins. It is deployed on the compute target on the cluster, and also the data store is mounted to the same cluster. In my experiment, I took the data directly from somewhere on the internet, but normally what you want to do, you want to store the data somewhere in the data store in the Azure ML workspace. And to save time, this compute is just mounted to the compute target. You see, the interesting thing here is that compute is separated from storage, and I can use different compute targets with CPU, with GPU, and apply them to the same data without moving the data. Then the script is started, and the logs from the scripts, they are live streamed to my computer, so I can theoretically observe what happens in almost real time. It's also possible to do it through the portal like I showed you in the demo. When the experiment is finished, it takes the output directory and stores it together with the experiment and with the experiment results in the Azure ML workspace. We have seen how we can easily submit scripts for execution in Azure ML, but what you would normally want to do in any practical data science task is to perform hyperparameter optimization. You would want to choose the parameters for your model which give best results. So in this case, you would want to run the experiments many times with slightly different parameters. And for that, it would be very convenient to be able to submit experiments programmatically. Also, in my example, I have downloaded the MNIST dataset from internet each time the script is run, which is not practical. So let me show you how you can store datasets in the same Azure ML workspace and how we can run Jupyter notebooks in the workspace to execute any related Python code. So let's start by exploring the notebooks section. I will create the new notebook here. And those notebooks, they are stored inside the workspace, and you can run those notebooks on different compute. So for example, now that I have created the empty notebook, I can choose the compute I would want to run it on. Right now, I don't have any compute created because the compute that I have is a cluster, and I need slightly different type of compute. So I will create a normal compute for notebook. I would call it NB compute. Again, I can select the different types of virtual machine, but normally I would not want a powerful machine here because a powerful machine is good for training. And here I would just want to run the simple Python scripts. So in this case, let's download the dataset from the internet and store it in the workspace. So I begin with downloading the dataset and storing the pickle file here in the local directory of the notebook. And then I want to upload this pickle file to the data storage. To do that, I will start using Azure ML SDK programmatically. So I create the workspace instance. The first time I do it, I need to perform the simple login procedure. I need to go to microsoft.com/device login and copy paste the provided code. So what it is my workspace. The Python code connects to my workspace. I need to do it only once when I execute this notebook for the first time. And then I have this variable WS for workspace, which I can use to manipulate the workspace. For example, I can upload the data there. You see, it's pretty simple code here. I say that I get the default data store, and I upload the data set to this data store. Then I need the training script. Let me, in this case, train a neural network model. So it would be the simple Keras two-layer neural network. And I would provide also some parameters to the script. So for example, I would be able to specify the number of neurons in the hidden layer or the dropout to use using the standard Python mechanism for providing parameters. So to run the experiment, I just need to run the script with different parameters. So normally, if you want to submit the training script programmatically, what you would do, you would put the script as the Python file which accepts parameters using standard Python techniques. Then one of the parameters would be the data folder that I want to use. This data folder is the folder where we would mount our data store. So my script would manipulate all the data as though they were simple files. So in my script, I would use normal Python file loading procedures to load the file. And that would be as simple as that. And then once I train the model, I can store it to the outputs directory for the reference. So the binary serialized model of each experiment would be stored together with the experiment. And I log the metrics. Let's see how it works in practice. So I have created the training script. Now I need to submit it. So what I do, I create the reference to my compute target. I just say cluster equals compute target and I specify the name. Then I create the experiment and I provide the required parameters. In this case, the only required parameter is data folder, and I just say use get default data store as the path. And then estimator is the object which defines the configuration in which my script needs to run. So in this case, I specify the compute target and all the packages that I need to have installed. In this case, Keras and TensorFlow. And then I say experiment.submit. So that's it, a few lines of Python code, and my experiment is submitted, and here you can see it up and running on the portal. And you can monitor the run on the portal and see the results. As we have seen already before, we have the accuracy here, and we can look in more detail what happened during the run. And in outputs plus logs, if we go to outputs plus logs, we can see that in the outputs directory we have our model. So here is the binary file for our model, which I can always download and use later on for inference. The way we have trained the model is typical for professional data scientists. However, Azure ML contains also tools for beginners. For example, Automatic ML allows you to start from the dataset and try different models on this dataset to find the best ones. Of course, it comes at a cost because it requires more computational power than if you were training the model manually, thinking about which types of model would work better. However, it allows people without any ML experiments to produce working models. And another way to train the model is by using the designer. By using the designer, you specify the graphical path on what you want to do with the data, how you want to train and test your models. And it, in fact, assembles together a package of scripts to perform everything. Again, you can use this tool without knowing any programming. Finally, once you have trained the model, either using the professional way or using AutoML, you can deploy this model to production. Azure ML allows you to have the registry of all models in one place. You can then decide which model you want to deploy, write a simple scoring file, and select the deployment target, which can be either Kubernetes in the cloud, or it can be a separate virtual machine, or even some modules on the edge if you are doing IoT scenarios. Now let's do our main example for today, which is training the generative adversarial networks on Azure ML to produce pieces of art, paintings like those. Paintings are produced based on the real paintings from the WikiArt dataset. WikiArt is the open collection of many pieces of art, which are grouped also by category. So what you can do, you can find the existing data sets derived from WikiArt on the internet, or you can use a special tool called WikiArt Downloader here to gather this data set. So I have gathered the data sets, for example, data set of flowers, something around 1,000 or 2,000 images. And then first thing I need to do, I need to store them into Azure ML data store. We have already seen how to do that using ds.upload. We have done this using the MNIST example, so I will not show you again how this is done. Let's instead focus on the way how generative adversarial network works to produce the. So GAN consists of two neural networks. The first neural network is called Generator, and what Generator does is that it takes the random vector of numbers, and from this vector it produces the image. So for each vector it produces the new image, a new painting. And originally, of course, without training it would produce some garbage. And then there is a second network called Discriminator, and the role of Discriminator is to be able to distinguish between the real painting and the one produced by the generator. And the discriminator would take an image as an input and would produce yes and no as an output. So you can imagine in the beginning when generator returns garbage, it would be very easy to distinguish between those. But then those two networks, they are trained together, so we can train discriminator to become better, and we also train generator to produce pictures which are less and less distinguishable from the human original image. And that is how both networks are being trained, and those networks are become better and better at producing and on discriminating images. So for our example, I would use the library called keragan, which is an implementation of generative adversarial network in Keras. And it implements the architecture which is called DC GAN, Deep Convolutional GAN. So it starts with a random noise vector. Random noise vector is undergoes several deconvolutions to produce the image. And then the discriminator is, on the contrary, it consists of a few convolutional matrices, which produces feature vector, and there is a classifier on top of that. That looks similar to this one. So generator is the model which applies several upsampling steps. So we start with a small feature vector, and then at each step we do upsampling. We increase the resolution, and we decrease the number of features, and we do convolution. And finally, the last size, the last layer contains 3 convolutional filters, which corresponds to 3 colors. And the activation function at the end is hyperbolic tangent. So it gives us the output in the range of -1 and 1. And it means that all our samples we also need to bring into the same range from -1 to 1, which is slightly unusual for image recognition tasks. And discriminator, you see, it does the opposite thing. It starts with the image, then does a number of convolutions and average pooling to make images smaller. And at the end, we have the layer with 1 neuron, which gives us yes and no, and the sigmoid is an activation function. So how do we perform training? That's the most interesting part, and I want to draw your attention to the fact that you have the code sample on GitHub in case you want to have a look into detail and if you want to learn more. So first of all, we generate a number of noise vectors. The batch size is the number of images that we use at each epoch to train. So we generate this batch size of noise vectors, and we use generator to predict this number of generated images. So GAN images is the array of generated images, and images is the array of images taken from our dataset. So this getBatch function gets another batch of images, so real and non-real images, and then we train discriminator to distinguish between them. We provide those images as an input, and we tell the model that we expect ones as an output for real images, and we expect zeros as an output for generated images. That's pretty easy. We get some loss, and then we need to train the generator. The way generator is trained is that we have the combined model, and we train the combined model of good and bad. The combined model consists of generator and then discriminator, and we train the model giving as an output ones. So we want to pretend those are real images. We want to adjust the generator so that it produces something which is less distinguishable from real images than before. So we freeze the weights of discriminator. You can see that in the beginning we use this discriminator trainable equals false. So discriminator weights are not changed during this combined training. We train only the generator. And that's how generator improves. And then what we also want to do, because we need to be able to estimate the quality of the model, and we can only do it visually by taking some generated images and looking at them. So every few epochs, we want to generate 3 random images and store them as the metric. So what we do here, we just take 3 noise vectors, we use generator to predict 3 images, and then we generate one sample plot with those 3 images, and we log it into Azure ML workspace. So because we want to run this experiment in Azure ML, we use this technique of logging. And logging can not only log simple metrics like a number, it can also log plots. We use the log image function here to log this sample into Azure ML experiment so that we can view it in the process of execution. If we see how it looks now in Azure ML, this is my experiment, which took something like 11 hours to execute. Let me select the one which is completed. So you see 11 hours. And in the result of this experiment, if we go to outputs, you would see all those sample images. Here they are. In the beginning of the training, when the network is not trained, it produces some kind of noise signal. Then if we go a few epochs below, you see that images become like a little bit more similar to paintings, but not yet clear what's on them. And then as further we go, the better results become. You see, those are things which can probably be considered similar to human paintings already. And we also store the models. So in the output directory, we can see actual discriminator and generator models being stored as the binary files. So once I do this training, I get this bunch of output files. I can retrieve the best model and I can use it to generate many more artistic images. So the way I can do that, I can interact with this Azure ML environment programmatically. So for example, I can create a notebook, and in this notebook I can say, okay, I want to get all file names which are associated with my run. So those would be all the files in the outputs directory. So models, sample files, everything. Then I want to select only those files which start with gen. So only the models for generator. And I can automatically determine the highest number. So like I take the last iteration as the best model. So I just determine the maximum value. And I load this file using this run download file. This takes the binary model from the Azure ML environment to my local computer or to the notebook if I'm using it from the notebook, so to the local directory of the Jupyter notebook. And then I can instantiate this model in Keras. I can load this model in Keras, give it some random number as an input, and view the results. So that's, those are 10 random images generated by our network, and you can see that some of them, like for example this paintings and this one, they look pretty good, while others they look like noise or something like that. So that's always the case with generative models. You can only select the best paintings, like a human being can select the best paintings. You cannot rely on the network to produce the best paintings all by itself. So as the conclusion, we have seen how Azure ML works. Azure ML provides a lot of useful features, like for example, grouping everything together in one workspace is very convenient. Then journaling all experiment results automatically allows you to keep track of everything without doing this monotonous job by hand. It can help you a lot with hyperparameter optimization, and it also supports distributed training, something I did not speak about today, but you can also perform distributed training on many machines on the cluster. To begin with, have a look at my blog post, have a look at this GitHub repository, and try to go through some simple steps yourself to experience it. And once you try it, I'm sure you would find the Azure ML a very enjoyable way of doing your machine learning tasks. Thanks a lot. I appreciate your attention to my talk. For more details, check out my website and my blog. And if you want to receive a painting generated by a neural network into your Instagram account once in a while, you can subscribe to Art of Artificial on Instagram and enjoy some fresh artificial art. Thanks again. My name was Dmitry Soshnikov, and I wish you a great conference today.